Dear colleagues, dear participants, it's a great pleasure for me to introduce our today's guest speaker, Dr. Gerard McCaul from Loughborough University, United Kingdom. Short information about his biography. So he obtained his PhD from King's College London in 2019. His scientific supervisors were Lev Kantorovich and Chris Lawrence. Shortly after PhD, he moved overseas to Tulane University, New Orleans, to the group of Professor Bondar. Uh, he worked as a postdoc there, and since 2019, in 2021, he obtained also double VM Keck fellowship and worked till 2024. Last year, he moved to Loughborough University to the position of postdoctoral research assistant and working there. His research interests are related to broad fields of non-equilibrium phenomena, open quantum systems, quantum control, driven imposters, if you're familiar with this concept, super oscillations, and recently last year, he also introduced the concept of quantum dynamical emulation. I'm very excited to learn more details about this. And with this, I would like to pass the microphone to Gerard. Please, the floor is yours.
Well, thank you very much, Andrew. It's a very kind introduction. I often forget I have a doctorate, to be honest, because the only person who usually mentions it is my dentist. So I was slightly shocked by that. But yeah, it was funny that you kind of mentioned in the introduction kind of some of my interests, and it's I'm sure it's the case for everyone, but you can feel like you're the way you approach research can be a little bit of a random walk. And I'm very excited actually today to be able to get the opportunity to tell you about something that was kind of developed over the course of the last year, which kind of I think is kind of it's hopefully something that you haven't seen before. So if like me, you're someone who's kind of someone who kind of craves a bit of novelty, this might appeal to you. Okay, so with that, it seems like as good a time as any to actually get started on the talk. So first, I think it's kind of important to set up the stakes of this, and I don't think I kind of need to spend a lot of time talking to this kind of audience about the idea that ground states, spectral gaps, properties of kind of quantum systems really matter, right? And they matter not just in terms of kind of describing reality, but in terms of information processing tasks. That one of the things that we want to be able to do with quantum computers is to be able to solve kind of problems beyond simply quantum dynamics, right? And in many cases, you can kind of think in terms of computational problems as things that you can kind of encode into a Hamiltonian. And this is a kind of little example of this here, where with an idea of kind of hybrid algorithm, where the thing that you want to solve is this thing called a kind of max cut problem, where you find the kind of the partition of a system that goes through the most lines. But when you think of it in these terms, and you think more generally of the kind of problems that you would like to solve, there is something quite restrictive about the notion of quantum dynamics, or at least in this kind of quantum circuit context. And that's the fact that you are kind of constrained by the fact that quantum dynamics evolves unitarily. Obviously, you have the Schrodinger equation, and this tells you, I d psi by dt is equal to your Hamiltonian operating on your state. And it has this unitary structure, which means that you preserve the probabilities of or you preserve the notion of probability for your states when you project them into a certain basis, and you get this oscillations back and forth. Very nice. The problem comes in when, as I was just describing to you, that there are all of these things where what you really want from to know about a system is not kind of its real-time dynamics so much as its kind of its ground states, its spectral gaps, things like this. Or maybe you want to kind of describe a more kind of dynamics that doesn't naturally map to unitarity. A good example for, I think, and that we'll kind of focus on for the rest of the talk, is actually imaginary time. Such a simple transformation, right? You just say t goes to minus I tau. But then on the level of kind of talking about a density, you find that this produces a really profound change in your dynamics. That, you know, this for a density matrix is a Liouville von Neumann equation, so it's just the commutator of H with rho, and yet when you make this change, you get an anti-commutator. And this fundamentally changes the kind of dynamics that you get. That is, in this picture, rather than kind of having this oscillatory behavior, you get exponential decay. And it turns out that actually this is something that you really want if you want to understand things like ground states and spectral gaps. And the simple way of kind of thinking about this is that, well, if I start from kind of, this isn't normalized, but you know, you can add your own partition function. If I start from a maximally mixed state and I keep evolving in imaginary time, as I keep going down through this, what I'm going to find if I express this in the energetic basis is that I get a kind of exponential weighting on all my eigenstates, such that as I go further and further, I'm getting closer and closer to a pure representation of the ground state. So there's this sense in which if I could just do these other forms of dynamics, I would have a kind of dynamical way of accessing equilibrium information. And that is kind of, in many ways, something we'd really like. So this is good. This is something I can do directly on a quantum computer. This is bad. I can't do it directly on a quantum computer because this transformation doesn't preserve the unitary structure of the dynamics. In many ways, it's kind of obvious, right? That this on its own is not going to preserve your trace. That's why you have to do this normalization. So we have this idea that imaginary time provides direct access to ground states and spectra, but we'll get to that later, but it's not a unitary transformation. So how can we use a quantum circuit to implement such a non-unitary operation? And just to kind of say, this is a thing that has kind of occupied people now for a few years of different ways of doing this. And these are all kind of really kind of nice, beautiful ideas about being able to do this. But what they tend to have in common is they're kind of a computer science way of thinking about it, that you take a unitary and you think about the variational approximations that you can make to get the one that most closely resembles this e to the minus beta h. And what I want to kind of show you today is something different. Let's say a kind of more physics-inspired approach to it that ends up with kind of some results which are kind of more constructive and potentially quite useful. But to get to that point, I have to kind of take one more kind of deviation, because what I want to be able to motivate ultimately is kind of where this idea has come from and how we can kind of use it. And to do that, I have to kind of go to something else entirely, which is kind of talking about open systems. Now, I don't know kind of the degree of kind of familiarity that everyone has with this, so I'll just kind of repeat it, and it may be something where, you know, I'm teaching my grandmother to suck eggs, but there we are. So obviously a complete system evolves unitarily. You know, this is the notion of preservation of probability. But one of the kind of interesting things is that you can kind of break the structure of that when you start thinking about the evolution of only part of a system. That is this kind of idea that you can have a unitary evolution, but then if you trace over some subsystem, the equivalent map that takes you that subsystem from the initial time to the later time has a different structure. And in fact, it's kind of the properties again that you want to kind of impose on this kind of transformation is that it has to be completely positive and trace preserving. Again, this comes back to kind of how we want to be able to interpret what the density is actually saying. A good example of this is something like the Lindblad equation, right? That you've got your kind of unitary part, and then you have this dissipative part here. Now, one of the interesting things about these forms of evolution is that you can always write them in what you could call a Krauss form. That is that this map actually looks like something that looks like what you call a kind of sum over unital operations, that these things in here are what you call the Krauss operators. And the condition that they have is that the sum of all of these things, mk dagger mk, has to equal 1. So it's like a kind of natural extension of the notion of unitarity. Moreover, if you started from a pure state and you knew what these Krauss operators were, you would never have to think about the density. All you would have to do is kind of say, I start from some state psi, and I think about the evolution of psi under all of this set of kind of Krauss operators, and then all of the expectations that I want to take out from my system, the density, I can still represent like this, but I just have to use kind of this set of expectations. And you'll notice that it's become something where it's still pure states, but now I am in some sense doing a kind of averaging over an ensemble. And this was an idea we kind of I explored with Dennis Bondar a few years ago. In that case, then the idea was actually just to try and kind of make a more efficient way of simulating a Lindblad equation, precisely because this idea is if you only have wave functions, right, you don't have to kind of deal with a kind of something of dimension n squared with a density. You just have to deal with a vector of some set of vectors of length n. And the way we wanted to try and exploit this was we don't know what the Krauss operators are, but if you kind of, I mean, you may have to take this on faith. If you take some kind of unitary operators of this structure and you just Taylor expand them out and you look at what this object looks like, what you will find is that when you do this Taylor expansion up to order dt squared, you actually recover the Lindblad equation. And what that means is that, okay, this is something where I could start from an initial state and I could think about these two forms of propagation as forming a kind of ensemble. Meaning that I start from some initial state 0, I evolve it according to each of these different operations, and I keep doing that. Now, well, the problem that I'll have is that this is going to grow the size of my ensemble with each step that I take. So the only other step that you have to kind of include is a sort of principal component decomposition, something where you say, I only want the number of states that I'm evolving to be of this size, so then when I've got that many, I want to do principal components, reorthogonalize them, and I just keep that many and start again, okay? And this is just the idea of trying to evolve a kind of Lindbladian evolution, an example of a non-unitary dynamics, only with a set of unitary operations. And it turns out that actually this kind of, this particularly for weak coupling, works very nicely. That you can kind of see here, this is an example of a kind of Heisenberg spin chain. And just plotting the expectations of the different spins. And in the top panel, you've got kind of using this method, ensemble rank truncation. In the bottom, you've got trying to use a kind of Monte Carlo way of doing it. This is this kind of unraveling, which also lets you work on the level of wave functions. And the point to say here is that, okay, you can kind of see where it can be pretty accurate, and also it can be much quicker than both the exact and this kind of wave function Monte Carlo. So that was nice. How does it relate to the original point that I was making about how can we do things like imaginary time? Well, just imagine you take these objects and you get rid of that bit on the front. That's like kind of getting rid of this unitary part of the evolution. And what you're left with is something that looks a little bit like that first equation that I showed you, this kind of block equation for describing imaginary time evolution. You've got this anti-commutator of rho with some other object. It's almost there. It makes you think, oh man, maybe I could do something similar with this to describe imaginary time evolution instead. And then I would have something that I could kind of directly put on a quantum computer. So this is the idea that kind of motivates what we're going to kind of spend the rest of the talk talking about. Now, one thing I should say, right? I'm aware I have a tendency to speak quickly, and I'm not always the most articulate person. So if there's any imprecision in my language or confusion, please feel free to kind of like turn on your mic and shout. Yeah, interrupt me at any time. Because yeah.
May I ask a question?
Yes, of course.
Regarding your procedure, so it doesn't have cumulated error, so you can propagate to very large times, and you do not see any difference between exact results.
It's a really interesting question. In some sense, it surely has some kind of accumulation of error on the level that I'm only doing it to dt squared, right? Mm-hmm. It will depend on the kind of the strength of the coupling, but then there's also something of kind of that makes it a little bit hard to understand how the errors accumulate precisely from this kind of step where you kind of drop some number of them. But for sure, like any approximation, it will have a kind of accumulation of error. What's surprising is kind of that it doesn't seem to kind of actually, part of this is to do with the structure, that this order isn't actually really dt squared. It's something like dt like cubed. I can't quite remember it, but if you work it out and you kind of look at it, you'll see that you have this idea that you only get certain, that this kind of structure, some orders of terms kind of will automatically cancel each other. This is something we'll see a little bit later, but this is part of the reason why I think it looks on this level like it doesn't have much error accumulation. If you took strong enough coupling, if you ran for long enough, of course you would see that.
Or if you increase the tau, right?
Exactly. Yeah.
Yeah. You see.
It is still at the end of the day a kind of approximation, but I guess one of the interesting things about it, and something we'll see here, is that it seems to be a kind of it seems to be a remarkably robust approximation, and I don't really have a good reason for why. So, what is the idea that I'm now going to try and hopefully spend the rest of the talk convincing you is not only feasible but kind of cool, and it's what I'm going to call kind of this thing of kind of quantum dynamical emulation. And what it turns on is it very similar in spirit to what I just showed you about this kind of Lindblad equation. It's this idea that, okay, what you want, there we wanted to do it just for kind of thinking about wave functions, but we don't have to be kind of constrained like that. Let's say I take a set of unitary operations on some state rho. Now notice, when I told you before about this kind of Krauss form, it had the relationship that if I've got a UI here, I would have a UI dagger there. That's part of what makes it kind of completely positive and trace preserving. But I'm going to say, I don't care about that. I'm going to let these UIs be anything I want. And that means that on the one hand, this isn't really a super operator. This isn't a physical operation I make on rho, but hopefully at the end what you'll see is that this doesn't actually matter, that with a kind of suitable interpretation, it can look like an ensemble of things that I can implement. And the whole idea of this kind of dynamical emulation is to consider this object from two perspectives. The first is to consider it as a generator and ask what kind of dynamics that generator corresponds to. And the other way of thinking about it is, let's imagine I apply this object many times as if I'm doing the evolution that the generator corresponds to. And then I take what I've got, which might not be directly kind of implementable, and if I kind of just put expectations on that and I shift things around, what I can find is that that thing that I get can be looked at as an average, an ensemble average of unitary evolutions. And that by putting these two things together, you will get a correspondence for how to simulate some form of dynamics purely out of operations that you can implement. Hopefully this makes sense. Now, how does it actually work? So let's start with this. And the target that I'm going to be looking for this whole time is imaginary time emulation. So taking this idea, let's start with how I can kind of take that idea from before and think about how I might be able to kind of create something where it looks like imaginary time evolution. So first of all, here's the idea that there's that kind of fake super operator L rho that I'm thinking of as the kind of the generator of my time translation. And then I start with kind of that object that I was kind of thinking about before, the bit that kind of sort of looks like just the dissipative part of that expansion for the Lindbladian. Now, if I Taylor expand this, it's all very nice. I get a couple of terms, and I get this kind of I get a d tau a squared here, and I get higher order terms. And if I were to think about what u rho u dagger looks like, it's exactly like the dissipative part of my Lindblad equation. Now, this is actually a disaster if you want to do imaginary time. If you want to do imaginary time dynamics, because one thing you know about this is that the dynamics is automatically trace preserving. And what I want is something where if I start from a maximally mixed state, 1, so it should commute with everything, I get, as I kind of evolve through this exponential structure. But clearly, anything that it kind of uses this kind of form as a generator is going to be problematic because it's trace preserving. Because if I started with 1, this would commute through everything and I'd just be left with a kind of 0, right? If you took the trace over this, nothing happens. So this kind of object cannot give you the kind of dynamics that I was talking about at the start. It's just baked into it. It's part of the structure of it being this kind of, the Lindblad equation is this kind of CP-TP map. So what do you do? Well, if you think kind of perversely and you don't worry about whether or not it kind of corresponds to something physical at this stage, you take a different approach. because the problem that you had was this minus, right? This is what makes it trace preserving. This is what kind of enforces all these properties that you would normally want. And it's precisely what you don't want if you want to try and make some form of imaginary time evolution. So you do something else. Rather than talk about you row you dagger, you talk about you row you. And again, it's almost the same kind of expansion, except at the order of d tau, where I want to do this, I've changed that minus to a plus. And this is the whole ball game, if you like, because now if I think about doing something where I still want my kind of density to kind of have kind of a mission character, things like this, and if I do you row you plus you dagger row you dagger, what I will find is that I get an equation of motion with a generator that is almost of the form that I wanted, right? It has this kind of block-like evolution, and it's plus something else. So whatever that something else is doing, at least it's not cancelling the work I'm doing of this kind of block-like imaginary time evolution. So that's the first part. Now, what is the corresponding differential equation for this? Like I said, if this is the generator, again, what I have to do is kind of expand it out, and you see that d rho by d tau, this is approximately corresponding to this differential equation. So if I take my row and I expand it in the eigenbasis of whatever this operator A is, so I've got, you know, these their probabilities on the diagonal and coherences on the off diagonal, and I've expanded my density in the basis of whatever this operator is, I can find fairly easily an equation for what these elements are doing, and it looks something like this. It looks a little bit ugly, truthfully. Like it has this kind of this structure that means you might say this doesn't look anything like the kind of the thermal Gibbs state that I motivated all of this with. It comes a little bit closer if I make that kind of condition that I start from a maximally mixed state, effectively like a thermal state at infinite temperature. Ignore this Z. This is the kind of the normalization. It is something you have to put in by hand. But if you start from this state and then you do your normalization, what you'll find is not a thermal state, but actually a Gaussian state. And this turns out to be really useful for reasons that we'll get to in a bit. But for now, just think, I've got something that has that same exponential structure, right? It's not quite the thermal state that I wanted to start with, but, you know, let's see what we can do with it. Okay, so with that in mind, let's now get, we have now this first way of interpreting that set of operations as a kind of infinitesimal generator whose solution looks something like that state that I first wanted to get. Now we go to the other side of this. What does it actually look like if I start from some density and I apply this kind of operation repeatedly, right? Because if applying it once looks like I've kind of moved myself forward by delta tau, applying it m times should kind of bring me out to whatever finite evolution I want. So the way to do this, turns out it's actually reasonably simple. I'm going to specify that we start from a pure state initially, because I can kind of generalize this to mixed states fairly trivially. And the whole argument is much simpler if I kind of start and I just say, this is some state, and the only condition that I need on it is that it's not an eigenstate of the kind of whatever operator I'm using as the generator. We'll call it the Hamiltonian from now on. So then I need a few more definitions. I can kind of think then that U is like kind of doing a step forward. So one way I can think about this is that if I've got some start site that I label by J, applying U to this steps it forward once in time. So, you know, if I apply U to psi naught, I get psi 1. This actually is the wrong way round. It would make sense if it was kind of for kets, but similarly, U dagger should be the adjoint of that. That is, if I'm at UJ, I should go back to UJ minus 1. So yeah, this is something I still haven't fixed. But you just think of it this way: that if I'm attacking a cat with U, it iterates it up by 1. If it's with U dagger, it iterates it down by 1, and the opposite for the dual space, right? That if I have a bra and I use a U on it, it sends it backwards by 1, and if I have a bra and I use U dagger on it, it sends it forward by 1. So that means that the structure of applying that operator as I showed you is actually, you know, it's reasonably simple to write down, right? That after one step, I'm going to have this thing of psi 1, psi minus 1, psi minus 1, psi 1, It's got a kind of relatively appealing structure. Now you can just from kind of the argument of, well, what's the maximum index that I could reach? Well, applying u each time can iterate it by 1. So at most, I already know that applying this object n times is going to have some kind of structure that has to look like this, right? That the kind of the furthest anti-propagated states have to be like n steps, and that within that, the smallest ones could be 0. But what I don't know is what the relative kind of weights on all of these things are. Okay, so this, hopefully you can kind of agree just from the structure of how I've set it up, kind of has to be the general form of rho after doing this operation n times. The problem here is that I've got no idea what the weights are. And if I could just know the weights, then I have a way of kind of joining these things up. Well, one way of kind of doing this trick is, it's always fun to go back to the kind of the inductive kind of reasoning ideas that you might have done in school, and just say, okay, this is what I get if I do it n times. So what happens if I just apply this kind of generator once more? And if I do it n plus 1 times, all I have to do is kind of rearrange it. Okay, I've got these new boundary terms, which already tells me something that, the value of this at the kind of boundary can only be 1, which kind of makes sense. And then in the kind of in the whole sum, I have this kind of relationship, which of course means that what I have for understanding what this is a recursion relationship. Before I go any further, I think some of you may have seen this already, but this recursion relationship actually is something quite famous in disguise, right? What is this recursion relation? Well, it's not totally obvious, because you've got these kind of this you're jumping by 2 indices, and you've got this factor of 2 in there. But when you look at it for kind of, if you sit and you stare at it for a little while, and in reality, you kind of try and do a lot of numerical simulations and find that there's some structure appearing, you might start to recognize it as the kind of recursion relationship that you get from Pascal's triangle. That is the kind of the factorial recursion relationship. So with that kind of piece of information, you can immediately then be able to kind of write analytically, what is the value of this kind of weight on it? And it's that it has this kind of slightly odd structure, but the point is to say, it has this factorial structure. So coming back again to the idea, left-hand side, figuring out what this kind of super operator corresponds to dynamically. Right-hand side, looking at what happens when we apply it repeatedly, and actually kind of really surprisingly being able to kind of get a be able to get a kind of closed form answer for what it actually looks like. And the final step then is just to kind of take this sort of object, which is kind of something that's kind of weird looking state, things evolved in opposite directions, and kind of just thinking about it on the level of expectations. That will let you kind of turn all this round, and rather than thinking about states, you can think about something in terms of kind of a weighted set of overlaps. That is, the idea here, the imaginary time quantum dynamical emulation, if you like, is to take that right-hand side that looks like this and say, but the expectations, all the things I would actually want to measure, are going to look like this, right? That it's a sum over something that I've got I've got this binomial weighting on it, and now I've got this object, which looks like a kind of overlap, right? It's a kind of state evolved in one direction, you sandwich it with the expectation, the operator that you want to take the expectation of, and it's the state going in the other direction. This turns out it is something that you can actually kind of implement in a quantum circuit. And for the experimentalists in the room, if you wanted to think about, is this something that you could kind of use? The real question, the only kind of physics that comes into it, the only place where quantum dynamics plays a role, is can you measure this kind of expectation? Incidentally, the partition function kind of also that you would need to kind of normalize this also has a kind of reasonably nice closed form here that you just replace this with 1. And so it kind of tells you something about the kind of the partition function of this exponential operator. So then, taking all of this together and joining the two sides, I get this kind of correspondence that starting from 1, I get this relationship that, this exponential of an operator looks like this kind of closed form sum of of something that kind of essentially looks like a kind of propagator. It has some odd things, like it has this root d tau, but the relationship is there. If there are any kind of mathematicians in the room, they may look at this object and go, it looks remarkably familiar. We will get to that. So I've given you this kind of fairly long picture of how it is that how it is that I want to be able to do this kind of form of dynamics, because I think it will give me direct access to things like ground states. And the way to kind of construct that is to think about it in two different ways, and then at the end join it up for a correspondence. But the question is, does that work? And one of the things that comes out of this that you can't really avoid is that exponential that you get has the square of an operator in it. And this at first glance can be a real problem. The reason why it can be a real problem is I already gave away the answer though. The reason it could be a real problem is, think about something like this: that you have a Hamiltonian and it has, say, n levels, and if each of those levels you can associate it to kind of some eigenenergy EJ, well, there are actually 2 to the n of these, depending on whether you put a plus or minus 1 label on each of those EJ, that would all correspond to the same squared Hamiltonian, right? So while e to the minus beta h will go to the lowest eigenvalue, the smallest eigenvalue, e to the minus beta h squared will go to the smallest algebraic eigenvalue. That is the one with the smallest absolute value, not necessarily the lowest lying eigenvalue, which... And you can always kind of think, okay, well, that's sort of a problem, right? Because now if I take my correspondence that I've worked so hard to get, and I just directly simulate it, and I compared it to doing the block equation, and this is for a really simple system like just a single spin, I start from some random state, and if I evolved it with the block equation, I would see, okay, as I go through imaginary time, the expected energy that I get is approaching the ground state energy, as I expect. If I use my correspondence, though, that doesn't happen. It goes somewhere completely different. So it's a nightmare, right? Like, they've done all of this work trying to get something, and you find that no, it doesn't do at all what you think, and it's precisely because of this behavior. However, something that we can exploit is the fact that we know that, in quantum systems and all of these things, when you put a global constant on any Hamiltonian, anything that you do, if you just raise the level, it doesn't actually affect your dynamics. It turns up as just a kind of a global phase on the state, and so it doesn't do anything. So we can kind of take this idea that, well, the problem that I'm having is that the Hamiltonian that I'm trying to kind of simulate, the lowest lying state of the square isn't corresponding to the lowest lying state of the system itself. But if I just kind of shift it up so that all of my eigenvalues are positive, then they'll connect to each other. And this is the idea. Instead of thinking about h, I think about h plus a classical parameter lambda. Now, if I now take this kind of correspondence that I've got, it's almost exactly the same, because the fact that I'm just using lambda means that kind of lambda is not something that I have to think about operatorially. I don't physically have to put it in my Hamiltonian. It just comes out as a phase factor here. And that means that the same object that I had before, the one thing that is kind of really, I need a quantum machine or some kind of experiment to be able to measure this, I can just keep that just the same, but I have an additional weighting on in the sum that I'm using. And here's an example of kind of, now, if you use this, if you have this classical parameter that, it's almost computationally free to take this, you've got these kind of expectations, and then you just sweep over values of lambda. What you would find is that here's the block equation evolving from some state, and here's this same correspondence being implemented now, but I sweep over different values of lambda. And what you can kind of see is that as I make lambda, send lambda to be kind of more and more negative, the rate at which it approaches this ground state gets quicker and quicker and quicker. Like, here's, if you like, a critical value of beta below which the expected energy of the Hamiltonian is kind of less than some amount to the real kind of ground state energy. And you can kind of sort of see this structure, that as I kind of take lambda higher and higher in the steady state, how far I need to evolve in imaginary time gets smaller and smaller. in order to be able to kind of distinguish that. A very simple kind of example to give you a sense of like what's happening here is just think about a two-level system. And if you think about the Gibbs state and you asked, okay, right, here's a two-level system that's defined by some kind of energy gap. If you thought kind of, well, what's the ratio, the kind of the probabilities of seeing E1 versus E2 in this state, you see that it's kind of, it's going to depend on the kind of the temperature, the imaginary time, and then also just the gap, okay? But if I have this thing under this square, this h plus lambda, and you work it all out, it now, well, first of all, you've increased your prefactor by 2, and then it depends not only on the gap, but also the average energy and this value lambda that you've put in. So you have a kind of tool at which to kind of, accelerate the kind of the difference between two energy states at a given kind of imaginary time. There is kind of more to be said about this, but I think that this is just to kind of give you a sense that okay.
May I ask a
Yes,
question?
yeah.
Don't with this green equation, don't you get the average energy for free by measuring probabilities then? Or so
Yeah.
it seems
So
that it's powerful, right?
yeah, and it's something to say that, you know, this is just to give you a sense of, because it's a natural question that would kind of you would think would emerge, right? Of kind of how can I, like, what resolution do I need for a given gap, right? That if you want to think about the spectral gap, things like this, and the point is that if you think about a thermal state, it's determined entirely by the gap, right? That the time, that the temperature you would need to reach to see it is the gap. But with this kind of emulation, you have this idea that, okay, and you're absolutely right, it's kind of about the average energy as well. You have something here where actually they're kind of, how distinguishable that gap is not dependent purely on the gap itself. You have this access to different parameters, and, you know, it also depends on the average energy. So, you know, you would like the idea that this average energy is not 0. That would be bad. But otherwise, you're getting this sense, let me say, that you have something extra here. You have something where you're no longer totally beholden to the kind of the equilibrium physics of the system itself, that setting kind of what your resolution is. Of course, one of the things about this is that I'm giving you this toy example of how you can get to the ground state. But of course, this lambda is a parameter, right? And what you've seen is that what happens is that when lambda is kind of equal to one of the eigenvalues in your system, that's the that's the smallest algebraic eigenvalue. That's what the system will approach to as you kind of continue this fake imaginary time evolution, which means you can sweep it, right? You can imagine taking this value and turning it up and down, and as you do, the state that kind of is being represented by this correspondence is going to change. It will, depending on your initial condition that you take, it will either it will definitely get your ground state, it will definitely get your most excited state, and then in the bands in between, the behavior of that actually entirely depends. It was to do with this kind of initial condition that I talked about. That, again, if I start from some random state, when you look at kind of what's happening in the middle of the bands, the state it's converging to is actually going to depend on the state that you chose, which is kind of, okay, it's a drawback, but at the same time, it tells you start from any state you like, as long as it's not an eigenstate, and you can get some of this information back out. This is kind of showing you, this is the same plot, but where I take that steady state and I kind of plotted these kind of eigenvalues going with lambda, the exact ones as dashed lines, and then I've drawn the kind of the prediction of the correspondence as this black line, and you can kind of see that in this instance, it's gripping to the bottom of each band as you go down. Taking a different kind of example, that was a kind of Ising spin chain. We did some small 2D kind of electronic ones as well, just to test a different Hamiltonian. And this one we did start from that kind of initial condition of 1. And there you can kind of see much more clearly that as you kind of trace this out, yes, it is kind of hitting each band at some point. Something that I kind of discovered only last week that I may kind of talk about, if someone decides they're interested in it and they want to hear about it, is that this actually tells you more than just the spectral information. It actually tells you something about the density of states. And if you want to know Why? Ask me about that maybe at the end. Okay. So I've kind of shown you now this correspondence. I've given you all of the kind of the I've given you this idea that with this, the fact that it kind of happened under a square is actually kind of really nice because you get this kind of parameter, this tool that you can use to sweep up and down, and that what that means is that on this level of expectations, you can take a system, you can evolve it, and if you can just measure this overlap with some accuracy, you have a kind of procedure for weighting that should give you all of this information. One really interesting thing about this, that speaking personally felt a little bit like I was closing a loop. I did my PhD on open systems, and specifically I did it on these things, things called influence functionals, which are these kind of path integral representations. And one of the abiding questions is how you can get effective descriptions of these. And it turns out, well, I'll show you. So let me go back to this correspondence, because it is it's an approximation, right? It has some error on the order of detail on it. And so it's natural to kind of ask, what happens if I take the large n limit of it? Now I'm showing you the correspondence for a particular initial condition where I just think about one and I kind of put my operators together. But the way I kind of derived it meant I could put other things inside. And that's an important kind of thing to note, because what I'm showing you here is that the large n limit of this for a given condition will generalize to something well known. But the point I want to emphasize is that I'm not sure if it's possible to go backwards from this and kind of derive the more general thing that I was showing you before. That's just one caveat. Maybe to protect the sense of novelty that I feel about it. But we'll continue. I'll show you this now. So large n limit. Take your factorial. Like if you know it, great. If you don't, I'm just going to kind of show highlight this for you here, that that you can well approximate this kind of factorial in the large n limit, very well in fact, by this kind of exponential function. And that if you kind of take this and you put it in, where now you write this object delta as your root 2 over n, you've got something which is kind of looking like something you can start to take the limit of. And in fact, if you take the limit of it by saying that x is equal to this j delta, you take the limit all the way to 0, this is what you get. This is called the Hubbard-Stratonovich transformation. Invented by Stratonovich, and I think Hubbard kind of happened to see it in some Soviet journal, and I think he was the first to write about it in English, so somehow that means he gets credit as well. There's no justice in the world. And this is kind of, on one level, you could say this is just completing the square. I happen to think it's kind of one of the most kind of beautiful integral transformations kind of in mathematics and physics. And the reason for that is that it's this really kind of powerful idea that, let's say you have some system with an evolution that's kind of highly non-local, that it's depending on itself in the past in a way that's kind of, you can't disentangle. Something that comes up a lot when you have these kind of influence functional representations of path integrals. That means that they kind of resist tracing out the thing and then being able to get a kind of effective evolution equation for the bit that you've got left. But what the Hubbard-Stratonovich transformation says, or one way of thinking about it, is that actually you can replace this kind of this non-local kind of dynamics where kind of history is kind of playing a role, with actually one that's completely local in time, but that is stochastic, and that the distribution function of that, or the kernel of that stochasticity, is related to the kind of dynamic response that you're seeing originally. The way you would usually derive it is actually very simple, right? It's as simple as kind of saying, I've got a Gaussian, and if I Fourier transform it, I've got two ways of interpreting that, right? One way is that this is actually a kind of an average of e to the ikx over my kind of probability distribution, and the other way is directly completing that square. And so this is the sense in which you can see something with k squared, and this kind of kernel sigma becomes something that you have to kind of average over realizations, but is kind of depending only on k. So you get this kind of idea. It's very useful in kind of open quantum systems. And one of the things that this kind of QDE says is that the fact that you can get this from a certain initial condition and a certain limit is that another way of thinking about this Hubbard-Stratonovich transformation is that it's not kind of just connecting deterministic to stochastic. It's sort of it can be obtained by thinking about kind of forwards and reverse evolutions and their relationship to equilibrium properties. So again, like if you're of a kind of philosophical bent, I kind of liked it, and I feel like this is a case where I've got kind of maybe enough time to just kind of give you a little bit of a flavor of it. Another thing that's kind of quite interesting, and again where I'm kind of flying off into wild speculation, is just to say another thing that's kind of cool about this kind of correspondence is that if I remove the kind of the expectation, if I just take that correspondence and I think about the expectation of it, I get this kind of funny looking object, which again is something that, you know, is kind of implied by the Hubbard-Stratonovich transformation, but I'm not sure I've ever seen it kind of written in this way, which is that particularly in the large n limit, I have on my left-hand side something that looks like this Gaussian object, something that is the expectations of this. Hopefully I've convinced you are clearly deeply related to the equilibrium properties of the system. And on the right-hand side, when I'm kind of applying my expectation, whatever that state is, it's going to look like this weighting with that state evolved in opposite directions. So that you can kind of think that on the left-hand side, here's something about the kind of the equilibrium properties of my state. And on the right-hand side, I'm asking something about its dynamical properties in terms of how much forwards and backwards overlapped. Like I'm kind of asking for a measure of reversibility, in fact. Now, if you know anything about stochastic thermodynamics, you may be aware of things like fluctuation dissipation relations, which, you know, first new thing in a century that came out of thermodynamics. Really kind of powerful, well motivated and kind of well established experimentally now. And they tend to come out of the notion of you have some stochastic system and you think about the probability of a trajectory going forwards against the probability of a trajectory going backwards. And this is where you get these kind of these fluctuation dissipation relations, right? It's hard for me not to kind of look at these two things and go, maybe there's a kind of link here, right? That it's the same kind of picture, but in some sense, this is a kind of more manifestly quantum thing that it's saying, because it doesn't talk about probability, it talks about the overlaps of states. It doesn't talk about work, because if you know your thermodynamics, you know that work isn't actually observable. It talks directly in terms of the kind of the system energies. And finally, if I really wanted to kind of push into the realm of like functional meaningless, I kind of point out that the thing that we could do to get back to our original picture is, and actually talk about Gibbs states, is to think about taking the square root of the Hamiltonian. Because in this picture that I've kind of presented for you, time kind of turns up under d tau, and d tau is always under a square root in the real-time propagators. So when I think about what happens if I reverse time, the natural way of thinking about this is h to minus h, because you can't do it on time because there's a square root there, but they should be completely equivalent. And what's nice is that in this kind of correspondence, it's completely symmetric, right? Because it's the overlap between forwards and backwards and complex conjugate, and h is under h squared. So h to minus h does nothing. But if I think about thermal states, the things that are kind of a product of irreversible dynamics, because I have to use h to root h, now I have no sense, nothing in my equations in which I can kind of take t or h to minus h without introducing a factor. That manifest kind of symmetry between forwards and backwards that's present in this case goes away when I start talking about the distributions that are the consequence of irreversible dynamics. Now, I don't know if that means anything, but I think it's kind of cool, so I'm mentioning it. Last thing I would say, turns out that this kind of, using that lambda trick, this relationship is actually also invertible. So there's a sense in which, oh, hey, maybe you can kind of say something about real-time dynamics, not in kind of directly in terms of these kind of more Gaussian states. I don't really, something I would like to play around with, but there's one of the things that I find interesting is that if you look at like kind of Lyapunov exponents and you ask their kind of behavior at short times, they do tend to have this t squared, this kind of exponential t squared structure. So again, something kind of interesting here that might connect to broader bits of physics. Okay, I've been speaking for kind of 50 minutes, and I feel like I've been I've been kind of imposing on the general of you coming here to listen by indulging in a flight of fancy. The last thing I'm going to do is go back to the initial thing of can we do this on a quantum circuit? The answer is yes. I will speed through it because it's more equations, it's more things to think about. The short version is yes, there is a procedure called a Hadamard test where you need one ancilla qubit, and if you follow this procedure through, what you will find is that the probability of measuring your ancilla qubit in the zero state is directly related to this overlap. If you're doing these phases, you need both the real and the imaginary parts of the overlap because there's that phase factor weighting. You can get that as well. You just have to change what this operator here is doing. So the natural thing then to say we had these kind of simple cases of trying it numerically. This is in a kind of one of the IBM superconducting qubit processors. I forget. And this was kind of this is the work of a PhD student over a month or two. So it was really surprising to see that if you've ever you ever seen what people are actually doing with these things, they're really finicky. They do not work very well. So it was a little bit of a surprise actually that kind of we could take the kind of this Hadamard test type thing and be able to kind of pull out expectations that worked well enough that we are kind of seeing exactly this behavior in a quantum circuit. Okay, I think that is about everything that I really wanted to talk about here. So hopefully now at the end of this talk, you have a little bit more of an idea about kind of this idea that been developing for the kind of last year about how you can kind of use this as an approach for the emulation of non-physical evolutions via unitary operations. Now, I should point out, not just imaginary time that you can do this stuff for. There's a couple of things that I would like to be able to do with it, but I won't talk about here. But even just thinking about imaginary time, when you kind of go through this, the structure that you get out has all of these surprising features that it turns out seem to be exploitable, right? That you can kind of get spectral calculations and things like that out of it. And it's completely agnostic to what you're doing it in. The only thing it requires is that you have you can find a way of measuring this overlap structure. That's it. And if you can do that accurately, everything else is kind of a analytically trivial weighting. Now, of course, I'm giving you the best possible view of this, but we know that the kind of the problem of finding a ground state is a kind of NP-hard problem. So there's no real free lunch here, right? So what's the sampling complexity of these overlaps? How is it depending on the parameters that I put in, like d tau and lambda? These are questions I don't have the answer to. And more than that, perhaps another kind of I won't say that. But other than to say, yeah, that there's kind of I'm presenting you the best possible view of this right now, but that's only because the harder questions I don't have the answers to, rather than that the answers are adverse. And hopefully I gave you a little bit of a sense of how this kind of idea can map more broadly into kind of other areas of physics. So it's another thing that makes you go, this is kind of fun. So yeah, that's me. That's the talk. I hope I delivered on the promise of something that you've not seen before. Now, of course, I did not do this alone. And another thing, as Andrew mentioned at the start, I spent 5 very, very happy years in New Orleans with my boss Dennis Bondar. So he was deeply involved in this work, as was his PhD student Jacob, who's now at MIT, and finally Alicia McGann at Sandia National Labs. Now, while they were not authors on the paper, I do feel like they did contribute very much to the kind of the development of the idea, and that's partially because we spent 3 months kind of before we left the US living in a van, tracing out this black line on the map, and that is my wife and my dog. So I have to mention them every time I give this talk, because genuinely they spent about 10 or 12 hours a day on the road listening to someone kind of mumble about forwards and backwards in time and overlaps and imaginary things. So I think they have to get credit every time. Okay, I think that's it. Thank you very much. If you have any questions, I'd love to hear them.
Thank you for a very interesting talk. Yeah, we are open for questions. You have reactions and you have question from Sergei Shevchenko. Yeah,
Okay.
please.
Thanks for the wonderful and beautiful talk, for the inspiring talk, I'd say. I'd like to ask you about the adiabatic quantum computation. When you
Sure.
were saying about finding the ground state, I was thinking, how can this be used for quantum annealing?
It's a great question, right? And it's something that I've thought about a little bit because one of the things about this is that the evolution that you're doing on it, right, is not physically changing anything, right? That you take a random state that you like and you kind of just bring it down in this way. Now, if you wanted to think about quantum annealing or all kinds of other things where a lot of the time you don't just want the value of the kind of the eigenenergy, you would like the state as well. And so I think one of the hard questions here is if you wanted to kind of compare it directly against something like quantum annealing, you have to think about a way of how you can do this in such a way that what you're getting out is not just being able to reproduce like the tomography of any state, being able to get its expectations, but having a sense that the thing that you've got at the end of this procedure is kind of a ground state or something like this. And that would require, I think you would need things like purification for it, essentially. But yeah, I think quantum annealing is kind of a great example of kind of comparison because there it's the idea that you're physically changing the Hamiltonian as you go, and you want to be able to kind of send it down to this state. In this instance, like the whole annealing process, right, is happening in emulation. That you're just sticking a given Hamiltonian, and then it's all in the ways that you kind of recombine it. I don't know if that answers your question.
Yeah, thanks.
So, more questions from audience?
Okay, may I ask?
Yes.
Does your results depend on the character of the state that you are following? So let's imagine that you are talking about the evolution of a localized state, especially localized state. Then it's okay. But what if this state is delocalized, but not only delocalized? I mean that probably everything will be okay if this is normal, say, plane wave delocalized states or something like that. But what about states that are near the mobility edge? So it is irregular. Such states are not following simple rules. Will your approach work or not? And if you please, can you explain will be some differences? And can your approach be insightful to distinguish between localized and delocalized states, especially near the mobility edge?
Okay. Another great question. And again, you're targeting exactly like the kind of the hard questions to ask, right? The things of kind of like, well, what is this actually saying? In some ways, it's a little bit difficult for me to answer precisely because it always boils down to this question of coming to this object that, I think generally people don't have a good sense of what it is, what its problems are yet. But that always I'm only talking at this level about kind of the expectations of things. And the only place where the kind of the quantumness of the problem comes into it is in taking that overlap, like going forwards and backwards and the observable and here. And so all of these kind of properties of localized versus delocalized, kind of what's happening at the mobility edge is in some sense asking, well, what is happening with the dynamics of these things in this place? Because if there is something that means that they're kind of like, that is making them hard to distinguish, you would probably see that again in this kind of, in the reconstruction, that it's a little bit difficult. And more than that, it's slightly strange because again, it's always turning on this idea of that exponential weighting is exponential weighting, right? That what I'm looking at is as soon as I kind of have whatever operator I'm looking at, and I think about the spectral decomposition of that, whatever the eigenvalues are, I'm going to get this kind of weighting on it, which might actually kind of come back to a slight point that I was thinking about before, and that you sort of mentioned it, kind of like, well, how much does it matter the state that I'm evolving from, right? What I'm starting from, because everything else is just letting that state evolve. So the state that I pick somehow should matter in this. It can't be an eigenstate of the observable that you're looking at, for precisely the reason that then you wouldn't get it, it just stays in that eigenstate. But there are all kinds of other properties that you could kind of think about the state. Like, what about its degeneracy? What about the density of states? How is this affecting it? And I can give you a slight argument for this, actually, of kind of that, in fact, you can learn something about those other properties from this. If you don't mind, I will just kind of bring up the one of the slides again to give you the example of what I mean. So I'll actually take the kind of the example here, which is kind of the simplest looking object. Okay, so I've told you already that if I take any state that's not an eigenstate, I evolve, I keep evolving at some value of imaginary time, I've got this exponential weighting and it all goes away. But you can actually think, well, what about these kind of regions where it kind of has to go from kind of one closest eigenstate to the next one, right? That what is happening here? Like, what is determining the shape of this curve in a manner of speaking? And you can imagine starting from let's say you have a two-level system, right, with some degeneracies G1 and G2, and you start from 1. What you're going to see is that as you're kind of going through, yes, like when you hit the closest eigenstate, you're going to see this. But in that interstitial region where it's doing this, it's always going to look like a sigmoidal shape. And it's going to look like a sigmoidal shape, but the place where that derivative is going to be maximal is actually going to be a function of the relative degeneracies of this level and this level. So you get a sense in which actually what this curve is telling you is if you took a derivative, you get a kind of, you need to do some processing on it, and this is something that I like literally last week I had this thought. You have some you can actually extract information about the density of states, not just from the kind of where these curves are plateauing, but what the derivative is doing between things. Now, it invites more questions as well, because how reliable is this numerically? What do you need these parameters to satisfy so that you can be reasonably confident about that? I've given you a very long answer to a question that kind of was about kind of localized versus delocalized and states near the mobility edge. I'm sort of covering for the things I don't know in a way of trying to talk more broadly and say, as I understand it, here are the things that I know it can do, right? Here is where real questions turn up in kind of how those things numerically are going to depend on those properties, right? And that's something I don't know. I would love to know. One more thing there I should talk about in that sense is that when I do this, I've got this oscillating term. It has some of the features that you might expect from a sign problem. And so another question is like, how do I know what the numerical stability of this is? Is that going to be somehow related to the kind of the physical system that I'm looking at and the properties of that system? Again, sorry, very long answer, but I want to kind of I want to be honest with you.
Okay, thank you.
Thanks. Maybe I would like to ask a question, continuing discussion with density of states.
Sure.
Would it be possible then to test something like Van Hoff singularities with?
Oh, that's a great question, and the answer is I've got no idea. But yeah.
It seems
Maybe.
like a good test.
Yeah,
For your
exactly.
method.
Exactly, right? Like, and This is one of the things I really like, that when you know, you talk about this and everyone's got their own kind of they will always have their own things that kind of like concern them in physics, right? The things that like they try and understand things through the lens of. And the great thing about something like this is that, you know, you present it to someone and they will use what they understand and ask that question of how does it relate to this? And that's immediately a research project, right? It's great. So yeah, yeah, I've got no idea, but I will add it to the list.
Just one comment: mobility edges usually appear near Van Hoff singularities.
So then there is there's another relationship then. Yeah. Yeah. See, very happy I got to give this talk.
And maybe one more question. You mentioned that there are other directions beyond imaginary time evolution for possible applications. Could you slightly give some hints about?
Sure. So I'll give two examples. One is still related to thermalization, but I'll take the more direct one. So one is thinking about error mitigation, which is this thing of kind of, okay, you have dissipation in your system that you can't control. What is a way of kind of what is a way of getting rid of it? And a friend of mine actually, they had a PRL kind of about 2 years ago, where they thought about this in the sense of, well, if you could just reverse the direction of time on the Lindblad equation, because of the structure of it, the sign on the unitary bit doesn't change in the same way as the sign on the kind of dissipative bit. So if you could add forwards and backwards in time together, you could cancel that dissipative bit and get a kind of form of error mitigation. And so one idea about this is, okay, let's use this same structure in exactly the same way. We know how to do Lindblad equations, and let's figure out, like, the kind of on paper, what are the things you would need to do and how would you need to combine them such that if the thing is actually evolving according to a Lindblad evolution, how do I combine these things in such a way that I kind of cancel that out? So that's error mitigation. The other thing is much more abstract, and it's to do with something else I worked on with Dennis, which is this thing called the wave operator representation. What it doesn't matter too much. The important thing is that it has this relation to an object called a thermofield double, which is kind of important in conformal field theories. It's supposed to be dual, but things I don't really care about, to be totally blunt. What I do care about is that this object is related to a thermal state, and it's something that you can kind of match unitarily. You can kind of, there is a quantum circuit that will do it unitarily. Now, using this wave operator thing, we figured out a way of kind of seeing this sort of evolution as something that evolves this kind of object, like something like a thermal state, but in real time. What's interesting about the transformation, though, is that in imaginary time, you're doing it at inverse temperature. So your ground state is at infinite time. Whereas this transformation, it turns it directly into kind of sort of real-time evolution. But the really important thing that it does is that it kind of maps your ground state to 0 time in this evolution. So, you know, you have a finite amount of time that it will take you to reach this object. You look at the kind of the structure of this thing and you go, actually, this is exactly the sort of thing that I can kind of evolve with this. And the fact that it's kind of, you reverse the directions of it means you can go backwards. Like, rather than thinking about eigenvalues, you can say, start with something that's thermalized, and now here's a procedure for kind of replicating this form of evolution where I've switched the sign of time. And if I know the temperature, I know how long I have to evolve for before this object now corresponds in the ensemble to the ground state that I had. So it's a kind of, let's say, a form of statistical cooling. So that's one more. Again, something you have to kind of see on pen and paper before I can convince you. But yeah. Hopefully you believe that I slightly know what I'm talking about with some of these things.
Thank you. I don't see other questions, so if it's not the case, let's thank our speaker for a wonderful talk and inspiring discussion. Thank you.
Well, thank you guys very much. It was a real pleasure.
Thanks a lot.
And I should say, yeah, if you have any questions or thoughts, please do email me. You know, I'm clear. Like, yeah, I love hearing from anyone about anything. Thank you.
Thank you very much for
All right.
openness. So all the best and goodbye.
Thank you very much.
Bye-bye.
Thank you.
Bye bye.
Bye bye.
Bye.
Oh.